All right, 9 o'clock. Ready to go? Where's everybody? All right, that's what we started talking about last class, right? This very nice L'Hopital's rule. And it allows us to go back and do limits again, right? And what are the conditions we need to use this rule? What do we have to have? When we're taking a limit, what do we have to have? 0 over 0 or infinity over infinity, right? So if we're taking a limit, doesn't matter what's going to what, we've got some function on top, some function on the bottom. If this goes to 0 over 0, or it goes to positive or negative infinity over positive or negative infinity, then we're going to do the limit again, but we're going to take the derivative of the top and divide it by the derivative of the bottom, and then figure out what that limit is, right? That's L'Hopital's rule. And so I showed you, out of our formula sheets, we have this formula sheet from the very beginning of class called the limit summary. We now have a new tool to do these two types of limits, right? And what I started doing towards the end of class last time was showing you this right here in green, this 0 times infinity, and how we can handle that. So what I'm going to do today is I grabbed some other calculus textbook off my bookshelf, and I'm just going to do some problems out of this textbook, some limit problems. So the first one I want to do is this one here. And then we'll get into the new stuff. I mean, we're still using L'Hopital today, but there's some new types of problems we need to look at. So I have not mentioned this, but all of these forms that you see here are called indeterminate forms. Indeterminate forms. Meaning that you can't determine what's going to happen unless you actually go and do something with the problem, like do L'Hopital or something. If you ever get 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 1 raised to the infinity, 0 to the 0, infinity to the 0. Any of those are indeterminate. And we'll talk about these bottom ones in a moment. Let's just tackle another one like this. So I have an indeterminate form right here. Limit as x goes to infinity. Then I have x, then e to the 1 divided by x minus 1. All right? And so what I'd like to know is, where's this headed, right? Does this limit exist? So let's just start by doing what we always do with limits, just direct substitution, which in this case we're substituting infinity, so we're going to be just having to think about what's happening, right? So as x gets bigger and bigger and bigger, do you all agree that gets big, right? Goes to infinity. So this heads to infinity. And then this is multiplication times. Now, 1 divided by infinity. 1 divided by something that gets infinitely big. What would that go to? It's a very small value, right? It's headed to 0. So this is headed to e to the 0, right? E to the 0 minus 1. That's what's happening in here. But any number to the 0 is 1, right? So this is 1 minus 1, and 1 minus 1 is 0, right? So this whole thing is headed to 0. With me? Now, when we have something that's really small times something that's really big, and it doesn't matter what order these are in because it's multiplication, you can always flip it. This is an indeterminate form. We talked about this last class. Something's getting small, something's getting big. You're multiplying them. Who wins, right? Well, what did I tell you have to do? Do you remember? Anytime you see this? Well, we can't use L'Hopital yet, right? We have to have 0 over 0 or infinity over infinity, which we don't have yet. Yeah, we're going to rewrite it. How are we going to rewrite it? No? Y'all don't remember? You're going to drop one of them down, okay? You're going to drop one of these two expressions down to the denominator. Now, when I say drop it, you're not really just dropping, you're rewriting it. So watch. I'm I'm going to choose to write the x in the denominator instead of right here. And I'm going to leave this one here because it's kind of complicated and ugly. So I'm going to leave e to the 1 over x minus 1 on top. On the bottom, I'm not going to write x. I'm going to write 1 over x, right? It's basically the reciprocal on the bottom. Do you all agree this is the same problem? Yeah? 1 over x, you could flip it up. The x would be up top, and then that's what we have over here. So that's just us. It's not being clever. It's just us doing something to make it turn it into a fraction. And now hopefully, well, it'll work every time as long as you do it right. This should be 0 over 0 or infinity over infinity. It should be. Let's check. We know what happens to this, right? As x goes to infinity, we already said that goes to 0, right? But now, because we wrote 1 over x on the bottom, not x like on the top, 1 over x, we know that goes to 0, right? And now we have 0 over 0. So we are now okay to use L'Hopital's rule. Questions? No, I'm going to turn this projector off. It's just blinding me. So you're going to now take the derivative of the top and bottom separately, right? No chain, I mean, no, not chain rule. No quotient rule here, right? No quotient rule. L'Hopital's rule is the only time ever in calculus that you can take the derivative on top and bottom of something. We're just going to do derivative top and bottom. So limit, I usually put an L here and I circle it to let everyone know I'm about to use L'Hopital's rule. I take the derivative of the top. So be real careful here. What's the derivative of e raised to anything? Itself first, right? So e to the whatever was up there, 1 over x. But then chain rule says now times the derivative of what's up here. And remember, 1 over x is really x to the negative 1, right? So if you take the derivative of that, you get negative 1 x to the negative 2, right? But that's really negative 1 over x squared. I think we talked about this a few times, like just try and burn this one in, what the derivative of this is. So I'm going to write that here, negative 1 over x squared. That's the derivative of what's up there, minus the derivative of 1, which is 0. So I don't have anything else up top, right? I don't like the way this negative is. I'm going to put it up here with the 1. There we go. All right, all over, now the derivative of the bottom. Well, 1 over x again, right? Take derivative of 1 over x, you get negative 1 over x squared. That's good, right? Because they'll cancel. And now we just want to know what's the limit as x goes to infinity of e to the 1 over x. And now if x gets really big, 1 divided by infinity goes to 0. E to the 0 is 1. Right, is 1. So this is 1. So this number, we're taking this limit. This number's getting really, really big, right? This number's getting really, really small. The bigger x gets, right? And what happens is neither one of these wins, so to speak, right? This one doesn't just blow up. This doesn't go to 0. It's almost like they shake hands. They're like, okay, let's just head to 1. Okay, they compromise. That's where it goes to. So if you were to actually graph that like a function, like go and graph that, we'll do it. What we should see is a horizontal asymptote. As we go out to infinity, the graph should get closer and closer and closer to 1. Let's verify that. So I'm going to graph y equals x times, in parentheses, e raised to the 1 over x, and then minus 1. There we go. So there's the graph. I'm also going to graph the line y equals 1, and I'll treat that like a dotted line so you can see it's almost like a horizontal asymptote. And as we go further and further out to the right, you can see that the graph gets closer and closer to it. Y'all see that? Questions? All right. So We did a few of these last class, right? If you have 0 times infinity, you take 1, you drop it. Now, what if you had wanted to drop this one and leave the x up top? Could we have tried that? Yeah, sure. Now, should we look at it? And I think when we look at it, we'll pretty much right away say, no, let's not do that. Like, I could have done this. Limit, x goes to infinity, leave the x up top. Now, if I take this thing and drop it to the bottom, look at what it has to become. It has to become 1 over that entire expression, right? Like that. Now, if you let x go to infinity, this will go to infinity, and this whole thing will go to infinity. So you can use L'Hopital here. You can. But do you really feel like taking the derivative of this?
No.
No, right? I mean, this is like a quotient rule. There's no easy way to take derivative of this. It'd be a little bit of work, right? I think this is easier, right? Derivative of this one, derivative of this one, pretty straightforward derivatives, nothing too crazy. So I would look at that and be like, nah, no thank you, right? Don't want to do that. All right, now if you are still a little bit unsure about this process, it's okay, because the next indeterminate forms we're going to look at actually require that we do this anyway. So let me show you what we're going to look at. What if we have one of the other indeterminate forms? There's 3 others that we need to look at. And I need you to understand why these are indeterminate forms. So we have this idea of 1 to the infinity. Now, when I write that up there, I don't mean the number 1, okay? I mean I have something in a base, okay, where this thing right here is headed to 1, to the number 1, and then I have an exponent, and that exponent is headed to infinity, right? That's what, when I write this down, I'm saying when you take a limit, you're getting this form. So the base wants to head towards 1, and the exponent wants to head towards infinity. Why is that an indeterminate form? Let's think about this. Let's say you have a number here that's headed to 1. Well, that means it's not 1, right? So maybe it's like, I don't know, maybe the number in here is 1.0001, right? That's a number that's close to 1, right? But imagine raising that to a number that's headed to infinity. So you raise that to the 2 millionth, let's say, power. This should get bigger, right? I mean, you're taking a number that's bigger than 1 and multiplying it times itself 2 million times. I mean, that should slowly get bigger, shouldn't it? Does this make sense?
Yes.
But we already know that if this number ever gets to 1, 1 raised to any power is just 1, right? So I look at it like this battle. You've got the base, right? The base right here, and it's like, hey, I want to be 1, right? I really want to be the number 1. And the exponent's kind of looking down at it going, yeah, you want to be 1, but I want to make you big. Like, I want to make you bigger. And they don't agree with each other, all right? So we can't determine what's going to happen here unless we do something, right? Unless we somehow implement L'Hopital's rule. So this is an indeterminate form. We don't know what's going to happen. The other form we have is 0 to the 0. Again, I'm not saying the number 0 raised to the number 0. I'm saying a number that's getting really small raised to a number that's getting really small. So again, this is a battle. The base wants to be 0, right? It's like, well, what's 0 to any power should be 0, right? Do you all agree 0 to any power should be 0?
Yes.
Okay. So the base is like, hey, I want to be 0. But the exponent's like, hey, wait a minute, hold on. Any number to the 0 should be what? 1. So see, these are at odds with each other, right? There's a conflict here. So we, again, don't know what's going to happen. We got to figure this out. And then the last one, infinity to the 0, right? The base is like, hey, I want to be big, right? I want to be big. And the exponent's like, nope, I want to make you a 1. So again, they're at odds with each other. What students will make a mistake, well, they'll misinterpret with this, is they'll think like anything they can think of is indeterminate. Like here's an example. How about How about 1 to the 0? What if you get this form? Is that a problem? Like, this is a problem, right? We don't know what's happening here. But is this a problem? The base is like, hey, I want to be 1, right? And the exponent's like, hey, guess what? I want to make you 1 too, right? We're going to help each other out. This will just go to 1. There's no questions here, right? This is okay. Make sense? How about if we have this? It's another one that students do wrong. How about 0 to the infinity? So the base is like, hey, I want to get smaller and smaller and smaller, right? And the exponent's like, well, I'm just going to keep raising you to higher powers, right? What happens if you take a really small number and raise it to a power? Does it get bigger or smaller? It gets smaller, right? So now that's different than this, right? Because the base here wants to be 1, and if you raise it, if you take a number that's a little bit bigger than 1 and raise it to a power, it wants to get bigger. But as soon as that number's smaller than 1, like this, it's going to want to get smaller. So it's like, hey, I want to be 0, and this one's like, I'm going to help you get there, right? I'm going to get you there faster. So this is good, right? We know that this heads to what? What does that head to then? 0, right? So it's not like any combination of zeros, ones, and infinities that you can think of are indeterminate. The 3 up there are the only ones that we have a problem with. Understand? Questions?
The tricks that you've given us so far are the ones that we would use for all of them?
I have not shown you how to do these 3. These 3 on the board I have not shown you how to do. Right now, the only thing we can handle, 0 over 0, infinity over infinity, 0 times infinity, that's the one we just did an example of. Now the infinity minus infinity, we did that way back in the day, and what we did there is we factored. But I'll show you an example of that just so we'll have one. So the 3 green ones on the bottom there are the ones that we don't know how to do yet, and the technique to do them is a little weird, all right? But it's, it is what it is, right? All right, so let me see. I've never done this problem before, so this will be fun. All right, we're going to take the limit. Oh, I've done this problem before, but not the next one. Limit as x approaches 0 from the right of x raised to the x. So we first have to determine, what is the issue here, right? Do we have an issue? So we have x raised to the x. Please do not confuse this with what we did last week, which is where I gave you a function, x to the x, and I asked you to find the derivative. Do you remember how to find the derivative of this? If you have something with x's here and x's here, you have to do log on both sides and then drop it and do all that, and then let me just show you real quick. If I did this, I would do natural log on both sides, right? I would drop the x out, and then I would implicit, right? I'd get 1 over y prime over here, or 1 over y dy dx. Over here, product rule, right? Do not confuse that with what we're about to do, all right? That's one of the most common mistakes I see on exams, is students mix up these methods. This is called logarithmic differentiation, and this right here is just the limit, all right? So we look at this and we go, okay, what's happening here? We have 0 to the 0, right? And this is bad, right? That's bad. Do you all see it's bad? I mean, I know it's bad because it's up there, right? But again, the base wants to get small. The exponent says, hey, I want to turn you to a 1. This is a problem. All right, so how do we do it, right? How do we handle this? Well, what we're going to do looks a lot like what we did there. We're going to call this limit, we're going to call it something. Let's call it y, okay? So we're going to create an equation. We're going to say y is equal to this limit. This is what you do. Anytime you see this or the other two, anytime you see those, you're going to call the limit y. It's your first step. Next thing you're going to do is take the natural log on both sides. So you see how this is already looking very much like that? Natural log of y on the left. Now natural log of the limit as x goes to 0 from the right of x to the x. Right? So let me write up here. This was the original problem, right? Limit x goes to 0 from the right, x to the x. That's the original problem. I realize that it's one of these 3 bad ones, right? So I write y equals the limit, right? And then I take natural log on both sides. With me? All right, we're not taking derivative, all right? We're not going to do 1 over y prime. We're not doing that, okay? What we're doing here is trying to figure out what this limit is. So there is a property of logs and limits that allows you, this next step, to pass this natural log through the limit and put the natural log right there, right? Now, I'm not going to get into that. It's back when our limit laws way back in the beginning of this class. So you're just going to have to take this on faith, that the next step is that the limit comes to the outside, and then the natural log goes inside. You have natural log of x to the x. Now, what do you think I'm going to do? Pull the x out, right? I'm going to drop the x out. I want to leave this here. But let's box it off so it's not confused with what we're doing. So now here's where I am. I've got natural log y equals limit x is approaching 0 from the right. Let's see, what am I doing? Dropping the x out, right? X in front of natural log x now. Yeah? Now over here, you would do the derivative and do product rule, wouldn't you? Do derivative of the left and right. It's not what we're doing. What we're going to do is see what this limit looks like now. So let x go to 0. Where does that go? This goes to 0, right? Times, now, natural log of 0. What's natural log of 0? Well, it's undefined, right? But this is saying what happens to the natural log function as we approach 0 from the right. This is natural log, right? What happens as we approach 0 from the right? You get negative infinity. So this is 0 times negative infinity. Well, guess what? That's what we started class with, right? A problem that's 0 times infinity. And it doesn't matter if it's positive or negative infinity. It's irrelevant because the negative can always come out of a limit. So here, we know how to deal with this, right? We're going to take, what do we do? Drop something, right? We're going to drop something, right? We're going to drop one of these down. Which one would you like to drop? The x? If we drop the x, it'll become a 1 over x down here, right? If we drop the natural log, it'll become a 1 over natural log. Which one would you rather take the derivative of? I would rather take derivative of 1 over x, right? If you do 1 over natural log, you're going to have to do a quotient rule. So the next step, see, I'm not taking the derivative on both sides. I am not taking the derivative on both sides. I'm leaving the natural log there. I'm rewriting that on the bottom as 1 over x. And now I'm using L'Hopital's rule, right? This is no product rule. It's not what I'm doing, right? So I'm going to use L'Hopital because now this is going to be infinity over infinity. Do we need to check it? X goes to 0, that goes to negative infinity. We know that already, right? But 1 over 0 goes to infinity now, right? So we do have infinity over infinity. So I write it this way. Natural log y equals, by L'Hopital's rule, limit x goes to 0 from the right. So I'm letting you know I'm using L'Hopital. I take the derivative of the top. What's the derivative of natural log x? 1 over x. And then what's the derivative of 1 over x? Negative 1 over x squared. We've done that 3 times now today. Now don't go trying to plug 0 in for x right now. This is an algebraic expression. We can simplify this, right? We have 1 over x. That's a fraction over a fraction. We can flip it, right? So let me do that right here. We have natural log of y equals, notice how I've been bringing the natural log the whole time down with me? It's like I'm working with both sides. Natural log of y is this, this, this. Now here I am. Limit x goes to 0 from the right. Let's see. I'm going to go slow here. It's 1 over x, but I'm taking the bottom fraction. I'm flipping it up. It's x squared over negative 1. And one of the factors of x cancels, right? So this just becomes natural log y equals limit x goes to 0 from the right. This I could write as negative x. Do y'all agree? That's just x, and then I have a negative 1 on the bottom. I just bring it up as a as a negative 1 on top. There you go. Yes?
So you only have to keep the L'Hopital's rule on that one little section?
Yeah, because what I'm trying to do is make sure that whoever's looking at my work knows that this line to this line, what I did.
Okay.
So I did L'Hopital to get from here to here. Once I'm here, you don't need, I'm not doing it again. So If I did L'Hopital again, I'd let you know though.
Okay, gotcha.
Yeah. All right, now this limit is not a problem, right? Let x go to 0, that's 0, right? So what we have here, careful, our answer is not 0. Our answer is that the natural log of y is 0, right? But what we wanted to know was what was y, right? We want to know what y was, not natural log of y. So how do you kill off natural log? What's the inverse of natural log? E, right? So what I'm going to do now is I'm going to take e raised to the natural log of y equals e to the 0. So I'm basically applying the exponential function to both sides of the equation. I'm not multiplying by e, okay? I'm using the one-to-one property of e in natural log that this can be converted over to that expression. And this e and natural log kill each other off, and you get y equals, and then e to the 0 is 1. So your answer is 1. So if I were to go and graph this, x to the x on the computer, if I graph x to the x, I can tell you that the graph of this function will get closer and closer to 1 as I get closer and closer to 0 from the right-hand side. Shall we check? You want to check? You want to see it? Or believe it? X to the x. X to the x. There it is. There's the graph. Do you agree that as you approach 0 from the right-hand side, it gets closer to 1? Yeah? All right, let's do another one. You will see this again in Cal 2. It'll just show up in the middle of another problem, and you'll have to do L'Hopital, or you'll have a problem like this pop up. All right. Let's see if any of these look interesting. Yeah, this one looks kind of interesting. Limit x approaches pi over 2 from the left. Whoa, okay. Of sine squared x raised to the tangent x. I'm pretty sure I've never done this problem. Looks pretty bad. All right, well, you've got to know what's happening, right, as x goes to pi over 2 from the left. So let's try direct substitution. Do you know what sine of pi over 2 is? It's 1, right? How do you know that? Pi over 2 is that angle straight up, right? Sine is the y coordinate. So the inside is 1, getting closer to 1, right? 1 squared, which should still be close to 1. So you have 1 raised to the, now what is tangent of pi over 2? As you approach, hold on. Here's what the tangent function looks like, right? Pi over 2 and negative pi over 2. This is tangent of x. You have vertical asymptotes at pi over 2, negative pi over 2. We are approaching pi over 2 from the left. So it's headed to infinity, right? So this top part is headed to infinity. Yes or no?
Yes.
Yes? Okay, so we have a problem. Yeah, this is a problem. This is an indeterminate form. That's the first one there, right? So if we have this, and we know that it's one of these weird ones with powers like this, first thing we're going to do is call this thing y. And then we're going to do natural log, and then we're going to drop the thing out front. Okay? So I'm going to call this thing y. Can I just call it y right like this? I don't need to rewrite it. Is that okay? Call it y. Bring in the natural log on both sides. Natural log y equals, I'm going to leave the limit outside right now. Let's see if I can do all of this. Tell me if this is too much. I can go back and back up one step if you need me to. Y'all know what I did there? Took the natural log on both sides, right? Natural log on both sides. Put the natural log right here, and I popped the tangent out in front of the natural log. So I did all that in one step. Is that all right with you guys? Yes? All right. Now, if we let x go to pi over 2, we know that this goes to infinity, right? And this goes to 1, doesn't it? And natural log of 1 is 0. That goes back to the graph of natural log. Back here, we should all be comfortable with the idea that the natural log function at 1 is 0 for all, well, for natural log every time. Okay, so we know that this right here, this is 1, that whole thing right there is 0. So we have infinity times 0. So we're going to drop 1, right? Which one do you want to drop? What's that? Yeah, let's drop tangent. Okay, let's drop tangent. If we drop tangent to the bottom, it'll become 1 over tangent, right? Which is cotangent, and I can take derivative of that, I think. I feel okay about that. If I drop the natural log, it's going to be 1 over natural log of sine squared x, and I really don't want to take derivative of that. So natural log y equals limit x is approaching pi over 2 from the left. I'm leaving natural log of sine squared x. Ooh, I have an idea. 1 over tangent x. I'm just realizing something that I feel like we should do it, but maybe we shouldn't, because I don't know if you would have seen this. Can we pull the 2 out front of the natural log? We can, right? Because this is really, that's really sine x squared, and that's sitting inside of the natural log. And so when I have, something to a power, the power can come out. Another way I could have seen that is that this is sine x squared to the tangent. I could have multiplied the 2 and the tangent together and just made that 2 tan x and pulled out a 2 tan x instead. I'm not going to do it, though, because we didn't do that initially. So let's just stick with it this way. But I'm starting to wonder if maybe that was a better approach. Okay, we good? I'm not going to take derivative of this with quotient rule. I'm going to rewrite that as cotangent. And then I'll use the formula on my formula sheets. Natural log y equals limit x approaches pi over 2 from the right of natural log of sine squared x over cotangent x. Now, this guaranteed will be either infinity over infinity or 0 over 0. You don't need to check it. If this started